This is what I'm calling the 0th video in the video series of Orbital Mechanics with Python, and you can think of it as a second introduction video. And the reason that I'm making this second one a year and a half after the first one is because this whole year and a half making videos has been a huge learning process for me. And there's a lot of things that I've changed that I wouldn't have even known to actually implement when I first started this video series. But before I get to that, we get more animations, just like I did in the first one. So this first one example of orbital mechanics around small bodies. So this central body here is an asteroid, and you can see the blue one is what's called a terminator orbit, which is the only type of stable orbit you can have on an asteroid because it's the small gravity of that, say, compared to the Earth. And this purple one, I chose some initial conditions to have very chaotic behavior, which I just think looks really cool. I'm going to make a whole mini series about orbital mechanics around small bodies because it's very interesting and very non-intuitive compared to what it looks like at Earth. As you can see with these you would never see these types of orbits at Earth. It just doesn't make sense. The second animation I have here, this is what basically the blue is the Earth, the green is Venus, and then that purple one is a midpoint between them. And so basically what Earth and Venus do every 10 years, when you plot out the midpoint, not the barycenter, but the geometric center of their two positions, they're actually going to carve out this rose petal pattern. And this happens every 10 years. So you can see the elapsed time here, how much time has gone by. And about every 9.5 years, we'll complete one whole cycle of this rose petal pattern, which I think is really cool. Orbital mechanics is a field that's very heavy on geometry and mathematics. So you're going to see a lot of things like this in orbital mechanics that just look really cool. And for the third animation, here is what an example of what, say, a satellite constellation looks like. Satellite constellations are really big and up and coming. There's a few companies that are doing them in order to provide faster and better internet all across the world. So this is just like a quick example that I just wrote up, kind of just to show to visualize, you just have a lot of satellites in orbit, and how would you actually control all these and have them be in a formation flight. This isn't optimized in any way, it's just an example that I just wrote up real quick. So, as far as what updates and improvements I have to the channel, so the first thing I want to say is these videos are not in chronological order. If I would have had to do it again, I would have done it in a bit of a different order, but I didn't. But that's okay because I spent a lot of videos on orbital perturbations, which is just one branch of orbital mechanics where there's just so much more out there, and I'm going to get to that. So, in order to improve that, I put in the video description a list of prerequisite and an optional prerequisite videos, which I'll show more. I started a bunch of sub-series playlists, so it's a better way to kind of navigate the channel. Just say sub-series of Keplerian orbital elements, a sub-series on orbital transfers and things like that. I have a new future videos list, which has plans for at least 100 videos. It's probably going to be a lot more. I have a lot of plans in store. And I also started splitting up videos between theory and software because a lot of the first videos, they're getting quite a bit long. If I could do them again, I would have cut them in half, really, but I can't do them again. They're there. They still have all the information, it's just that they're a little bit long, so you can also think about just splitting up in chunks if you think one is too long. So this is an example of what the video description would look like, where I have a prereq videos and then the optional prereq videos. So some of them have a lot. Say for video 24, orbital escape trajectories, there's just a lot of videos that you'd have to watch in order to understand. So the way I'm doing it is the prereq videos are what you need to see in order to be able to understand what's going on, and then the optional prereq videos are what you need to see in order to be able to implement yourself everything I'm doing in the video. But you can see it's not chronological. So video 15, all it has is a prerequisite introduction video, and then there's some in between, say video 6, where there's just one prereq, but then if you want to understand what's going on, you probably want to watch all those. So list of future videos. I'm actually really excited about this because there's a lot. I really have a lot here. So here it is. I'm not going to say them all because there's so many, but you can kind of just read through them and leave any comments below, just so if you want me to explain one, or if you really just want to see one, and I can make them just in any order basically. So I have an Earth orbits category, particular type of Earth orbits, eclipses. Maybe I could even do how to predict an eclipse at Earth. Orbital transfers, there's a bunch of those. Asteroid redirect missions, so say we know that an asteroid's coming at us, how can we redirect it so it doesn't impact the Earth? There's been a lot of methods proposed. Orbital mechanics around small bodies, like I said in the first animation. Our solar system, basically our solar system is really cool, and there's a bunch of stuff to talk about it, like our moon. So why do we always see just one side of the moon? Why is it tidally locked with Earth? And Mercury, so Mercury's orbit actually can't be explained with just Newtonian mechanics. You have to go to Albert Einstein for relativity because it's so close to the sun, that gravitational pull is so strong, it's bending space-time so much, it can't be explained by Newtonian mechanics. I think that's something that's really cool. Circular restricted three-body problem. So as we're getting to the Artemis generation, doing sending people back to the moon, this is an incredibly important problem that needs to be analyzed and solved. Reference frames, so just kind of the definition of a bunch of reference phases. I can go deeper into that, inertial and non-inertial. Parallelization, because there's a lot of things, orbital mechanics can get computationally heavy, so if you can take advantage of more cores of your computer, you can do a lot more calculations in less time. I'm also going to add a different actually series altogether, so orbital animations with Python, kind of just go over how you create all the animations that you see. Optimal orbit transfers, again, its own field of study that I can do a sub-series on. And I'm very excited, I am going to get to spacecraft attitude dynamics and control. So it's going to be kind of a prerequisite to know some orbital mechanics, and then after that, I can get into kind of like the attitude dynamics, because that's a whole different field of study that's very interesting. You can read all those video ideas that I have, and then numerical methods with Python. I'm just making another series because, again, this is something that's really important that I haven't seen anyone else cover. So then I'll just show, to end it real quick, this is what my channel page looks like now. So I have different sub-series: Keplerian orbital elements, orbital perturbations, ephemeris data, basic trajectory data, orbital transfers, Lambert's problem, and numerical methods. So that's how I've got it all sectioned out. So that's it for this one. In the next video, oh, that was the next slide. In the next video, you tell me, what's the next video going to be? I'm thinking is Pluto a planet, because part of the definition that NASA gives for a planet has to do with orbital mechanics, or I could do a Homans transfer. Obviously, I'll get to them both at some point, but leave down in the comments which one you'd like to see. So yeah, just basically let me know which one you'd like to see next. Make sure you hit like and subscribe for the YouTube algorithm, and thank you for watching.